if I like you guys said, the industry in general, whether it's flour or oil, is very conservative in material selections. It's taken years to come up with material specs that we have for either turbine blades or oil equipment. To replace it with a different material, would be difficult. So it would be nice if I could buy any brand of laser metal printer that then I can use the material from different vendors. So how many materials suppliers are there supplying powders in this industry that are compatible with oil industry materials?
You can address this, but I want to go general first.
Okay.
So if you're familiar with the powder metallurgy industry, count up the suppliers, that's how many suppliers there could be. And even though you're buying private labeled material from EOS, 3D Systems, or another company, it is just being repackaged material that's coming right out of PM industry. So we really don't have an inherent limit, and they may void your warranty if you put somebody else's material on there. On the metal side, we really aren't that bad. They are more open platforms. I think the worst case is one vendor will charge you $40,000 to open up the parameter set to run a third party's material on there. So the good news is we do have a rather open platform on metals, more so than we do in plastics. The bad news is the latter part of your statement, any machine, any material, you take a given metal, a specific alloy from the same vendor, same particle size, same distribution, same everything, and put it on vendor A's machine and put it on vendor B's machine, both of them using laser, you will get two different results because it's how they process it. So we have some inherent challenges there, because even if I can give you your PM supplier material and put it on a machine, I can't guarantee you're going to get the same characteristics. You are going to have to still requalify.
So think of it in the two lights that we started talking about. Prototyping world evolving to manufacturer versus manufacturers offering a new technology solution. In the prototyping world, this came up as the Vic and the Razor model, right? So powder is the money. They're not gonna make it easy for you to substitute their cash cow in the prototyping mentality. But as we move into manufacturing, we know manufacturing is not going to tolerate that behavior. So as we get more and more manufacturing applications, the pressure will get higher and higher. But we're in that middle ground right now. We're in the chicken and the egg. Everybody's kind of saying, well, when you buy a trainload of material, I'll open up the parameters to you. When you buy 5 or 10 machines, then I'll give you more latitude on material side. So we have this push-shove relationship going right now. What I'm excited about is as you look at these new equipment manufacturers bringing out tool heads, they understand you don't want to buy another gantry. You want to repurpose the gantry you have. They also understand that you want to use whatever material you know how to use, but the burden's going to come on you to figure that out. As Todd was saying, you're going to have to qualify that, understand it, understand the issues with particle size, distribution, and energy going in, and how you're putting that energy in, what that does. Long term, you got to know that game anyway. So get serious about it, understand how your value proposition is going to go, and jump in the water, because it's the new pool. And you're going to have to figure that out if you're going to be in this industry.
I think the same thing happens in private industry too. You make a business case for this powder being melt used in their machine. They are going to help verify that data and work with you to do it, especially if you're going to buy a machine. A lot of machines are like $625,000 on the high end, things like that. So they want to sell that machine and make 2/3 profit. So they got a best position to do this. And I was at the Freeform Fabrication Conference in Austin last year, and we had universities came up with like 48 different new alloys they have tested and make other machines. And we're seeing more openness above the OEMs to use machines based on the business case for those particular alloys.
I wondered, you were talking about replacing parts that you might have already in your manufacturing in a critical situation, but wouldn't the additive process be usually less strong than what the original material would be?
That's an easy softball one. Give that easy one to Todd. Actually, sorry to point you out on this one. Please ask questions. What you stated is not necessarily true. It depends on the technology platforms. And in some cases, we do have inferior mechanical, thermoelectrical properties. Other cases, it's not true. Depends on the technology platform. In the metal side, that's usually not true. We're very near to, or even better than what you're getting out of billet or out of castings or machine components. Our challenge is that we're just subtly different. Microstructure is subtly different. The porosity you see is subtly different. And those subtle differences may not be an issue, but no one's done the testing and the evaluation to say you can ignore that. I was telling somebody earlier, I did a presentation at the Metal Powder Industry Federation's annual trade association meeting, and it's all PM stuff, powder metallurgy. And one of the guys walked up to me and he just laughed. He said, "Your guys' problem is you don't know how to sell holes." I said, "What do you mean by that?" He goes, "Our parts aren't fully dense, yet we're using it for axles and drivetrain components and automotive and all that." His message was, you don't have it qualified as to what's an acceptable limit before parts fail. And therefore, since you haven't had it qualified, everybody's going after 100% density, which is really not realistic. So we do have, in the metal side, I would say we have very, very strong, very attractive properties. And as was indicated, we got the opportunity to change those anywhere throughout the part to give you exactly what you want in certain spots. We just need to get to the point of all that testing, all that research, all that qualification to give you the comfort to say, oh, minor porosity, not a problem.
And I'd like to just add on to that, Todd. You got the exact right point. Today we're a little lazy about our design. You start with a billet, you don't want to take any more machine time at that than you have to. So you leave a lot of material there that's not necessary because it costs you too much to get out. So today what we're doing with the additive technology is you have to get more aggressive to make it a cost benefit. So you get more aggressive, you take a lot of that material that you're carrying for no reason and for convenience of manufacture out of the part. So you'll find you have margins. So you're doing trades in this space now that you have to be smart about. But it's a great point. I would say, Todd, the one thing that he's probably heard of, and it's rightfully so, our materials are not always isotropic as a billet. Just like your rolled material, just like your extruded material, and you understand those and have been working with those for years. We have a slightly different anisotropic behavior. You got to understand that, you got to know that, you got to design it in your part and design your part for that.
So, one thing, if we can characterize the energy industry, is a lot of times you have facilities in remote locations across the world, land and sea. And we have a parallel right now with our U.S. military. In forward bases and on Air Force and Navy carrier groups, they have direct metal machines on their building replacement parts. And some of those are on aircraft. I hope they know what they're doing. They say they do. So that's encouraging. And I think there's a lot of applications in energy for those kind of remote, because you don't want to have to send a replacement part halfway across the world and take 2 weeks to get there at an absorbent amount of cost. And you know, right now in some of those oil rigs, for example, we have little machine shops and things like that. In the distant future, maybe not so distant, we'll see some 3D machines on those places they build parts.
There are groups that are working towards that.
Yeah, I think it's something for every manufacturer in this industry to start thinking about your strategy when what we know is happening is distributed manufacturing. So instead of even down to UPS and Staples and OfficeMax, they're already thinking about an Amazon. The reason they're in this game is they see the opportunity for distributed manufacturing, make on spot. So you're going to have to rethink how you're going to design product, get paid to have it manufactured somewhere else. And the opportunity to have that impact will be real inside of the next 10, 15 years. So shifting that business model to handle distributed manufacturing demand, your customer will demand that, will be a very difficult challenge for everybody. It's something that's coming.
What is being done to improve the additive manufacturing speed? You know, the biggest drawback right now for additive manufacturing is the slow speed.
I can take a little bit of that. Depending on what materials, if you're strictly talking the metals, I mean, they're adding more lasers, they're adding higher temperatures, they're adding, it depends on the provider of the machines. They all know that time is an issue. A lot of that does kind of weave with material that you're talking about. Some of it, you know, there are some limitations that they're working with. As far as the time, I mean, even in the past 5 years, there is a change in how long printing takes for something as simple as a plastic part. You've gone from filament-based to jetted materials that are cured by photopolymer materials cured by UV. They've gone from single lasers, low intensity lasers, to multiple high intensity lasers. So they know that that's an issue in the industry. As I say, I've only been in the industry full on for 8 years, and I've seen the machines change probably 3-4-fold in that time frame. And I'm sure in metal, you guys can be more specific, but they're definitely looking at that. It's definitely something that is going to change. And now with a lot of the jetted metal materials, you were talking from hours, or sorry, many hours to 2, 3, 4 hours. So that technology is being looked at.
The trend right now is that very similar to what you do in the subtractive world. If you have a very large billet and you say you're going to go at that with a 10,000ths cutter, and you're going to be there for months, right? But you don't. You go in at it with a big mill, you go plowing through it and knock everything down, and come back and fill out the pockets. What we don't have today is a technology that has multiple build heads. We don't have the one that does 10 pounds an hour, followed by one that does a few pounds an hour, that can go in increments to provide you the surface finish and contours features you want. What we're seeing, though, is that with these tool end effectors coming online, we're getting those technologies now. In addition, they're adding on 5-axis toolpath control. One of the problems we had was 2D toolpath. It was very difficult to control it. But now we can actually flip that, and with 5-axis, you can come back in and put those features on secondarily. One of the I try to resist giving company names, so one of the NC machine companies migrated the two technologies together, and layer by layer, they go in and densify quickly so they can go much, much faster and do a cleanup cut with a single cutter, very small precision. It's an excellent combination of the two technologies, getting very, very precise surface and good surface finish, but much faster densification. So these are the kind of trades that we're seeing in the industry come together, get married up with these harebrained, cool ideas coming out of new people thinking based on manufacturing demands. You will set, we need your voice in this conversation to tell us what are those, what are the trade space, what can we compromise on surface finish and speed to get you more rock. So great question, great.
I'm really regretting using that word harebrained because I have a feeling I've been labeled as, hey, the dude that said harebrained. And just to clarify a little bit, since he didn't name technologies, Bill didn't name technology, so what that strategy is, high rate deposition, bulk deposition, and I don't care how accurate it is or how ugly it is, because I know I'm going to come in with a machining pass. So that is one strategy. You mentioned new materials from X1. You know, we do have platforms that are, for large parts, are already rather speedy. Now, X1, a lot of people may not think of because their original strategy was after the 3D printing process, additive manufacturing process, put it in a furnace, burn off binder, sinter the metal together, but leave the pores and infiltrate with a lower melt temp alloy. So you had a 60-40 blend, which is really hard to qualify. Well, they're now following the path of powdered metal and doing a full sintering and densification. So, what are they running? They're probably running for big platform machines, and I'd say no more than a minute a layer for that. And you say you do 10,000 layers, you do the math, you could have some really massive things in a matter of hours. So we do have some, but if you're thinking laser-based, which is the most common right now, on a bed of powder, yeah, they are really slow. And what we're doing right now is adding multiple lasers. Our challenge there is you can't just dump in more energy and expect great results. The whole equation just starts to blow out. You get too much thermal dissipation, you can't control it. So we do have some physics and some chemical, physical, and other aspects coming in that are serious barriers for us, which I think for speed we may end up seeing brand new technology ideas. So instead of trying to improve laser-based technologies, it's out there. We're going to see that come up in the plastic side of the world. There's some guys out there that have demonstration videos where we're looking at 3 inches an hour of high-resolution plastic parts, where we're currently at half an inch an hour is a fast machine. So we're going to have to give metals a little more time. But there are people thinking about it, as indicated, and we will see progress. How fast, how soon, I don't know.
Yeah, well, I think the technologies are here. Look at Lincoln Electric has a hot wire technology coming. For you guys, if it's not on your radar list, write it down. Lincoln Electric hot wire. You need to know about it. For you, it's pounds of material, not ounces of material. So it will be where you will be adopting. This is technology that's hitting the street now, not in 5 or 10 years. So these are things that are coming out that you need to keep an eye on, because it will increase the speed and handle your larger parts. It's currently much better at refurbishment, replacing material, than it is at building completely, but you can do it.
So there's a lot of talk about qualifying materials and reaching material properties, and we want to know how these additive materials are going to act. So companies are doing this internally, and they're spending the money on it, and they don't want to share that data. So for somebody who's starting out doing that, are we shooting for the mill properties that we currently know? Is that our goal that we're trying to reach, or are we just printing millions of specimens and sort of setting our own standards? What type of approach is recommended for that?
ASTM 42 is the standards committee to get on. That's the groups that are coming together to say, how are we going to do this better? America Makes is the industry that the government stood up to share information. So think of America Makes from a technology 1 to 3. You're locking up your IP, don't take that to that audience. Once you're past 3 and you're ready to start doing some implementation, you got some things you think you can share with others, take that there. That's when you pay $1 to get $10 of value. All right, because you get 10 other people to say, I'll put in $1 and we'll all test those together, and then we'll get that information together. That's really, in my opinion, I'll get on my soapbox for one moment. China invested $400 million in one institute. That institute is going to aggregate a library of data that is going to surpass everybody in 5 years. We invest our money at a federal level at $1 million, maybe $10 million a project. That's distributed knowledge with no hooks, no clawback to bring that back to the general public that you paid for. And as industry, we're replicating that over and over again. And we're going to lose that race if we don't figure out that our IP, 1 to 3, our IP should be locked up. License it. You're going to find people in these relationships that will license that technology from you. So you're going to find customers. And at the same time, you're going to only spend $1 on $10 or ideally $100 worth of value. So as industry, if we'll come together in these ways, we have opportunity to keep up with people that are being infused that are going to really do some damage if we don't counteract.
Just as a point, I'll agree with you 100%. Where do you start and how do you get there? Every company that is working towards manufacturing, or actually it's mostly manufacturing, the rapid prototyping, I mean, it's there out of the box.